This lecture should be recorded. This first part was not, unfortunately. I had forgotten to press that button. I apologize for that. The rest of this lecture is recorded. So, and the notes will be uploaded. So, now there are certain special open sets that are important to know. First of all, the empty set. And just for those, if you haven't done a lot of set theory, so the empty set is the set that contains no elements. And the empty set is open. And well, the proof is kind of vacuous. There are no elements, no x in the empty set, so there's nothing to check. So recall that the condition was, for every x, there exists a delta blah. But if there isn't an x, that means that the condition is automatic, because there's no x that we need to check. Now, another example of a set that's always open, quite vacuously, is the full space X. So if X is equal to omega, the full metric space X, then this set is open. And well, the proof is, well, fix an X, and take any delta. Delta, say delta equals to 1, then well, bx1 is contained in X because it consists of points in X. So we are done. So there's a good question. Is this kind of like if the assumption is false, that the implication is true? This is very similar to that, indeed, because whenever you have a for every quantifier, especially for every quantifier inside a given set, then you could just say this is the same thing as saying if X is in omega, then there exists a delta positive such that Bx delta is contained in omega. So if you take a point inside, then there exists a little bit of room. This is another way of writing openness. And now if we write here the set that we are concerned with, namely the empty set, then indeed this assumption is false always, and that makes the implication true. The full implication is true. This is indeed exactly analogous to that. So that's a very good point. This is an instance of that kind of an argument. So it is a little bit sort of, sometimes people say that this is vacuously true because there's nothing to check, or that somehow it's a, yeah. And whenever you have a condition actually that's formulated with, that starts with a for every quantifier, then the empty set will automatically satisfy said condition. So thank you, Zach, for that question. Now, to talk more about properties of openness, I just want to quickly remind you, this is, you've seen this in other classes, about unions and intersections. So union of a set consists of those points that are in X or B. The intersection of the sets, denoted by a cap, consists of those points that are in both. Now, notation that you might be slightly less familiar with is if you take a union of n sets, then this means that it's sufficient to lie in one of these sets. So there exists one set. So it exists, in this case, this is a union from 1 through n. So there exists one index such that you belong into the set. But there's no reason for the index set to be finite. And here I allow a general index set I. A lot of the time you'll have I equals n, and that's mostly what you want to do. occasionally you'll want bigger sets. So here I allow any set to index. Then union over those is just all those x's such that there exists one index, I, in this abstract index set, such that you belong in the set. So these are fairly intuitive notions. And similarly, we can define intersections over an arbitrary index set by insisting, well, intersection normally is that you lie, intersection of two sets, you lie in both sets. So intersection of n sets, or in general of some index set I over some index sets I, is all those points x that lie in every one of these. So there's a for every quantifier here. And maybe the only thing that I want to highlight here is that everything you know about logic and quantifiers plays a big role when you're talking about unions and intersections. Why? Because hidden in the definition of these sets are quantifiers. For every, there exists and or. So everything that goes into proving something and something else, or something or something else, or there exists, or for every, that's exactly the same when you prove that something about these intersections. Just to fix a term, whenever I say finite, I just mean somewhat informally that you can list the elements of the set. This is not a rigorous definition. Defining finite in a rigorous way would take us far too afield from this lecture and doesn't really serve a big goal. It would be a topic of set theory or some other course to define properly what it means to be finite. But now I just mean that you can list the elements. There are 10, 100, or some finite n number of them. But why I introduced this notation is to be able to state this theorem. So suppose I have some index set I, and I have some collection of open sets. Then I can construct new open sets in two different ways. So if I take an arbitrary union of open sets is also open, and that works for any index set I, whether finite, infinite, or anything. But the second one only works for finite index sets. If I take a finite intersection of open sets, here finiteness is crucial, and this is also open. So unions, you can do anything you want. Intersections, you are more limited what you can do. So as a quick picture, imagine if you have a ball and you attach another open ball to it, then what do you get? You get everything inside the outer boundary of this thing. That's still an open set, intuitively, because it doesn't include its boundary. But let's prove it from the definition. So when you prove something is an open set, it's a statement involving a for every quantifier, so we have to take fix x inside our union. We have to use the definition of a union. So there exists an I such that x is an AI. Well, we have to use our assumption that our sets are open at some point. So at this point, it makes sense. So this set x belongs into AI now. So there exists a delta such that, let's call this delta I now, because we will choose almost a different delta, but this time it will be the same. But I want to highlight that it connects to AI. There exists a delta I positive such that Bx delta I is a subset of AI, because AI is open. And okay, so we know that there's a little ball contained in AI, but because this is a union, that little ball will also be contained in the full set. So we will actually choose the same delta. So choose delta equal delta I, then Bx delta is contained in AI, which is contained in the union of AI. So we found, for every x, we found a delta such that this is contained in the union. So union AI is open. And here we only needed, because we could use that single delta that that we found, this worked fine. Looking at this proof for intersections involves a difference. So if we fix now in an intersection, and our I is now finite for the second part, well, we have to use the definition of the union and openness. So for every I this time, we have that x is in AI. And if we use for all of these, so that means that every I equals 1 through n, that means that for all of these finitely many I, we have a delta I, since for all I, AI is open, there exists a delta I, but this delta I can depend on the set I, a set AI that we're choosing, such that Bx delta I is contained in AI. Well, this ball is contained in AI. Now we want a ball that's contained in all of them. So motivated by that, we choose delta to be minimum I equals 1 through n, delta I. Now these delta I are n finitely many positive numbers. This minimum therefore exists and itself is positive. So it makes sense. This step uses finiteness. This is the point where the proofs are different, because we have to do a different choice. Here we have to choose a finite delta. But once we are able, the conclusion is very similar after this. Well, Bx delta, so for every I, Bx delta is contained in Bx delta I. Why? Because delta is less than delta I, less than or equal to. And Bx delta I is contained in AI by choice of delta I. So what we get is that for every I, Bx delta, because here the left-hand side does not depend on I, is contained in AI. So this ball is contained in all of these. And then we can conclude that Bx delta therefore is contained in the intersection of AI, our finite intersection. And that's the end of the proof. So in both of these cases, we have to choose a delta based on the definition of the union and or intersection, as the case may be. Any quick question on these? I did go over these quite quickly, so yeah. Are these also provable by induction? Yes, you could prove it by induction. Yeah, there's well, the second one is provable by induction because we have a statement involving n. So you could prove it for 2 sets first, and then you could add more sets in the process, because indeed this is the same thing as intersection from I equals 1 to n minus 1 AI intersect an. So probably many references probably prove this by induction. The first one you cannot prove by induction because this is not necessarily finite. So first one induction, the second one not. Good question. Okay. So because we have still a number of things to discuss. So this The next two sections, we'll just give a picture of what this concept means. We'll give a definition, a formal definition with all the quantifiers in place. And then I'll give a quick example. But we won't, unfortunately, at this point, go further into these steps. But what boundary is trying to encapsulate is you have some set, and most of these sets I'll draw in the plane, and the boundary point should be something that lies at the frontier of that set. And the crucial property that we have is that, well, it contains points outside. And it also contains points inside. And this property should not depend on the radius. This should hold for all radii. Because a boundary point at least seems to satisfy that property in common examples. I mean, there might be some other features that you might feel essential to be a boundary point, but this is certainly something that plays a role in being a boundary point, that no matter what radius you take, you see some of the set and you see something on the outside of the set as well. Indeed, so if A is a set, then we define the boundary of A to consist of all those points X, and these can be points in A, outside of A, that doesn't matter. They have to be points just in the big space X, such that for every radius positive, and this time I don't really think of it being small, so I'll use R. If I take the ball BXR, its intersection with A is not empty, and its intersection with the complement is not empty. So this means that you can find something in A and the second one means that find something outside A. Okay, so this is the definition. Every ball intersects, centered at that point, intersects both the A and its complement. So a simple example of this would be, say, if we take the half open interval A, then the boundary of A would consist of 0 union 1. So certainly, say, if X is equal to 0, say, and if R is positive, well, there exists a delta in the interval 0R, so a very small delta, so that X plus R, well, actually, we don't even need this. This one's easier than this, sorry. Make this clearer. So we're focusing on X equals 0 and R is positive. Well, X equals 0 is inside the ball BXR, and it's also inside A, because this is the half closed interval. Now, if I take X minus R over 2, then this, which is the same thing as 0 minus R over 2, which is negative, then this is not in A, because we're only taking non-negative numbers, but X minus R over 2 is still in the ball BXR, because we only subtracted R over 2, namely X minus R over 2 minus X is equal to r over 2, which is less than r. So what we get is that x minus r over 2 is a point in the ball intersected with a complement. So we found a point there, we found a point there, and this didn't depend on r in any way, so this held for all r. So indeed, we proved this part. One would be similar, slightly more technical because it's not inside the set, but very similar to that. Now, boundaries can be very complicated. This one I won't prove, but a good exercise is if A is the set of rational numbers and as a subset of reals, then boundary of A is actually everything. Because, well, if you take a ball, because any ball, this is x minus delta, x plus delta, contains both points in Q and in R over Q, take away Q. So both rational and irrational numbers are contained. So boundaries can be fairly weird. Sometimes they're intuitive, but in other cases, they're a little bit less intuitive. So that's why we need a precise definition so that it works in all of the cases. At least we have some clear sense of what is a boundary, regardless of if the set is nice or not. Okay, so that was boundary. Now, interior and exterior. Well, and we might include some parts of the boundary as well. For the set A, these apply for for any kind of set A. And interior and exterior, they try to capture this idea of, well, if you're not a boundary point, then there exists a radius that's either inside or a radius that is outside. But now this time it can depend on the radius. A small radius might work, but a big radius might not work. So the definition reflects that. The interior is defined as, it's denoted by interior of the set A, and A is a subset of metric space here, is all those x's such that there exists a delta positive, such that the ball centered at x of radius delta is contained in A, and the exterior is defined by there exists a delta such that this set is contained in the complement. So that's the formal definition. And along with our example, let's look at 0, 1. Well, the interior consists of all the points. Well, they have to be in the set because x lies in that set, in the ball centered at x. And they have to be those points where you have a little bit of extra room. And well, you don't have the extra room at the boundary point 0. So one could prove, analogous to what we did above, but using this different definition, that the interior of A would be 0, 1. And the exterior, well, consists of those points on the outside of the set with a little bit of room around them. And that would have to be all the negative points, but also all the points strictly bigger than 1. So minus infinity to 0, union 1 to infinity. But 1 is not included here because 1 is a boundary point. So there exists a no matter the radius, you will intersect both sets. So that's the case where interior and exterior seem more intuitive. But okay, if we have A is the rational numbers, then interior of the rational numbers is empty. There's no ball contained in it. Similarly, the exterior of rational numbers is an empty set. Now, could 0 be included in the interior? And this was asked related to the first example here. No. So if x is equal to 0, no matter the ball I take, it intersects the complement. So we have from before, I'll say it here clear, from before, if x is equal to 0, then, and r is anything, any r, then the ball centered at 0 with radius r intersects a complement in a non-empty way. That means no ball is contained in A. So 0 cannot be in the interior in this case. 0 is a point of the set, but it's not in the interior. In fact, there's a statement, a theorem, that I won't now have time to prove, that first of all, if you have any subset of X, the full set X can be decomposed into 3 parts: the interior, the boundary, and the exterior. And these are disjoint sets. The interior intersected with the boundary is empty. The interior intersected with the exterior is empty. And the exterior intersected with the boundary is empty. So this is a so-called partition of the space into 3 different parts. And if you look at the definitions of these, then you can show that if you don't belong into the boundary, you either belong into the exterior or interior. And then if you belong in the interior, conversely, you get that. And you can also show that if you're an open set, a more familiar, say, this is often used in calculus and the multivariable calculus to define an open set. Omega subset of X is open if and only if the boundary of omega intersected with omega is empty. So a set is open if it does not contain any boundary points. So colloquially, a set is open if it doesn't contain any boundary points. So this, both of these are very important theorems, but at this point we will not prove these. So we will talk more about these later, though, in other contexts, and certainly in the discussion. Now, the final thing that we need to define are closed sets and convergence. And those are things we will a little bit do some proofs. So I want to remind you, and this is, if you got confused by these boundary exterior and exterior, I invite you to focus on this and sort of refresh your mind, because this is a little bit different and allows us to go back into some things that you should be more familiar with. So if we are in the real line in R, in 131A, we defined 2 things. Converge, if a sequence converging, and one could also define this other sequence converging to 0. And these are the same thing. And I will prove these by writing out just what both of them mean. And then you see that these conditions actually mean the same thing. Well, the first condition means that for every epsilon positive, there exists an n such that if n is greater than or equal to n, then the xn minus x is less than epsilon. Well, what does this other one mean? This time, our sequence of numbers is this distance, and it's converging to 0. So it means that for every epsilon, there exists an n such that if n is greater than or equal to n, then absolute value of xn minus x minus 0 is less than or equal to epsilon. But this here is nothing other than equal to xn minus x. Because 0 is 0, you can take that out, and absolute value is already positive. So this is exactly the same condition. The quantifiers are writing both of these conditions out. They are verbatim the same, so they are equivalent. They are the same condition, but in slightly different disguise. The nice thing about this is that the second condition is something that we can use in a metric space, because this only involves the distance. So this second condition only involves the distance. dxnx, which was defined in the real line as xn minus x. So what we do, this second condition we can generalize to a general metric space. So if xd is a metric space and xn are points in x, a sequence of points, then we say that limit n goes to infinity, xn exists and equals some x infinity. Let's just use x to match what we wrote above. And this includes, so this statement includes existence. If, well, for every epsilon positive, well, let's write it actually without the epsilon. So if limit and then goes to infinity of the distance xn to x is equal to 0. Now this is a sequence of real numbers, whereas this is a sequence of points in x. And then this can be written, now this converging to 0 just means that for every epsilon positive, there exists a capital N such that if n is greater than or equal to n, then distance xn to x is less than or equal to epsilon. These two things are the same statement. Just a clarification of the first. Now, one proof, at least, I want to give on this concept, and then the definition of closed. So, uniqueness of limit. Now, this defines what a limit means, but there's no reason that this limit wouldn't be unique. So, if x and y satisfy, limit n goes to infinity xn equals x, and limit n goes to infinity xn equals y, then these are equal to each other. So this is uniqueness. This is often very useful, but it's not immediate from the definition because we don't see immediately that x is equal to y. But what we can show is the following. Proof. Well, let's fix first an epsilon positive. Then there exists an n x such that if n is greater than nx, then we get that distance from xn to x is less than epsilon. I'll put an epsilon over 2 here. There also exists an ny such that if n is greater than or equal to ny, then the distance xn to y is at most epsilon over 2. And why we do this is we want to compare ultimately the distance from x to y. Now this is some real number. This is now less than, by the triangle inequality, the distance if we go via the sequence xn. And if we choose, if n is, say, maximum of nx and ny, we get to choose n, because this is true for all n. So let's just choose n equals its maximum. And then we get, from these assumptions, here and here, we get that this is less than epsilon over 2 plus epsilon over 2, i.e. equal to, which is then equal to epsilon. So just a little bit more space here so I can conclude this. So what we get is that for every epsilon, this positive, whatever this number dxy is, it is less than or equal to epsilon. But there's only one non-negative real number that satisfies this, namely, so often this is said epsilon is arbitrary. So the distance is equal to 0. You could think of this also by sending epsilon to 0. This middle part does not depend on epsilon, yet it's less than or equal to epsilon for a positive amount. Therefore, it has to be equal to 0. Okay. Now, I want to just say that I don't expect all of these conditions to set in, but I want to introduce them now so that as we discuss them in office hours and elsewhere, as you see more videos, as you talk with the TA, they will start to cement. But now we are just fixing this language and getting a little bit of used to it as we have the rest of the course to talk about these concepts a lot more. But what we'll end the lecture with is the definition then of a closed set, which is best expressed in terms of convergence. And that's why I had to introduce this convergence, which itself is important. So we say that a set E is closed if for every sequence of points xn in E, it holds that if limit n goes to infinity xn exists, and we denote that limit xn equals x, then that point belongs into E as well. So colloquially, E contains the limit of all sequences in E. So this is about the end of the lecture. So what I will now just give 2 examples and I'll answer some questions. And because I screwed up with the recording at the beginning, I will just read over that again so that the students who are in Asia and who elsewhere, say in Europe, who are not here now, have still that resource of me speaking over that. You can tune out at that point, or if you want a refresher, I'll do that. But so just some simple examples. Let's take the interval 0, 2. So the worksheet problems are not graded in any way, but the homework, yeah, the homework is the only thing that is graded. The worksheet problems are, so when we have the office hour tomorrow, for example, I will certainly try to discuss some of those things there as well. It is there to give you another resource of some interesting problems and also to stimulate some discussion between you, each of you. But so to finish this explanation, if this is my interval, if this is my set E, now we call this a closed interval. Let's verify that it's also closed in the sense that we just defined. So if xn is a sequence in 0, 2, and if limit n goes to infinity, xn equals x exists, well, we want to show that x is also in E. Well, what we know is that xn is less than or equal to 2 for all n. So therefore, by a theorem from last class, from 131a, we know that the limit also is less than 2. And similarly, since xn is bigger than or equal to 0 for all n, 0 elements, we get that x is bigger than or equal to 0. In conclusion, we get that x is between 0 and 2. Therefore, x is an element of E. And that shows that E is closed because this works for all sequences that converge to that. So that's an example of a closed set. Now, if we want an example of something that's not closed, let's take the half-open interval that we saw above. An example here that doesn't converge, well, xn is equal to 1 minus 1 over n. Well, limit, these are all points in A for all n natural numbers. But limit n goes to infinity of xn is equal to 1, which is not in A. So we found one example of a sequence where the limit is not in A. One counterexample. So A is not closed. So there are other tests and ways of checking that a set is closed, but this is the way that uses directly the definition of the set. So we covered many things, but any questions that people want to discuss right now? But as said, we will get other chances to discuss these as well. So all balls, whenever I talk about a ball, it has a positive radius. We haven't defined a ball for a negative radius. So BXR always consists of points that are at a positive distance from that point. Because distances are non-negative, we don't know what is a negative radius in that case. That's another way of thinking about it. But good question. This is an important point to remember. So whenever we have radii, those radii must be positive. Other questions? All right, yeah. And I wrote earlier, bigger than or equal to 0. Yes. So whenever I write these conditions, I'm careful to write strictly bigger than 0. Now, I allow in a definition of a ball, I do allow the radius equal to 0, but it doesn't really it doesn't give you an interesting ball, because what would be the ball of radius 0? It's all those points such that distance x to y is strictly less than 0, but there is no such point. So this would be an empty set. So even if you allow the radius 0, okay, it doesn't lead to a logical inconsistency because the existential quantifiers insist on positive radius. Well, the only place where we have to be careful about that is the boundary. But indeed, there we have to put our positive. So the ball of radius 0 is not an interesting object. For all practical purposes, you can exclude that, and you can just even define balls with positive radius. But the way that I define the interior, exterior, open, and closed, it doesn't cause an issue that we allow a 0 radius ball. Other questions? Okay, so as said, well, okay, there's one more. So when the set, so well, short answer to this question. There's no reason to have a ball of radius 0. So you could define, and this is perfectly consistent with this class, R is positive, X is in X. Then the ball centered at X of radius R is all those Y such that dxy is strictly less than R. This is the only case that is relevant for the definitions. Now, if we allow the 0 radius, if R equals 0 is allowed, then our ball would have to be empty with this definition. But in the interior and exterior definitions, we insist there exists a positive delta. These are positive. So we don't allow a 0 radius to be in the definition. So while a ball can have 0 radius in the terminology, when we define interior and exterior, there's a strict inequality there. Yeah. All of these definitions, here, the boundary, and the open sets that we defined last time, they involve a strict inequality. But yes, this is a very good question, Albert, in that you want to be careful about this, because indeed, otherwise you could lead to anything being in the interior and exterior. So we have to prevent it somewhere. Any finite set is closed. That is a correct answer. Yes. That's a very good example of a closed set. Yeah. Finite set in the usual topology. You can define topologies and distances where they are not closed, but this is not an issue in this class. So finite sets are always closed. Actually, in a metric space, finite sets are always closed. So you don't have, actually in this class, you don't have to worry about this at all. In other classes, you may need to. Other questions? So at this point, I will switch from these questions. Feel free to leave, because I will just do the boring thing of going over the first 3 slides here again for the students who will look at these slides later. So the homework is due next week, Friday, April 10th.
Can I ask a question about, like, in the beginning, the proof of the balls in the metric space is open? We did that in discussion yesterday, and the TA used something in the beginning and then he corrected himself, but it kind of didn't make sense. He used the minimum of the distance between x and r and the radius, and that distance, if that makes sense. And then he was like, no, actually the difference between the distances works on its own.
So this is what yeah, I think so. Yeah, the difference just works in this case.
So, but what if the 2 points are very close to each other, like that? Wouldn't that distance be like too large for a radius?
Well, that's a reasonable instinct that you might want to make it smaller, but to assuade any doubt, let's look at the proof. Did we do any mistake, or does it read properly? Well, if I take a point here, z, well, distance x to z, this inequality, this is just applying triangle inequality, which holds for all distances.
Oh, okay.
Yeah,
Okay.
distance x to y is defined as s, so that's an equality. But distance y to z is strictly less than delta. Well, okay, symmetry, because I chose to write this in this way. So that's strictly less than delta, which by our choice is r minus s. So s plus r minus s, which gives us r.
Yeah, so it still holds at the end
It
because
still
of
holds,
okay.
yeah, the difference does work
Understood.
in this case. Your concern, it's a reasonable thing to be worried about. So you could always put a factor of 2 here, r minus s divided by 2, or divide by 10, because it's enough to find one delta.
Yeah, got it. Okay, thank you.
But yes, so, and homework is due next Friday. Okay. So, yeah, see you later. But if you want this quick review, then stay along. Feel free to stay on. So this lecture, that most of it was before, it was defining these different concepts for metric spaces, and due to a recording technical issue, I missed the recording of the first part, and I will just read out or recall the main ideas of this to make these notes a little bit more readable, is that recalling from last time, the definition of an open set. For every x in omega, there exists delta, positive, such that the ball centered at x of radius delta is contained inside omega. And this has come up many times. Delta really needs to be strictly positive here. Otherwise, this definition would not make as much sense. Any set would then be open if we would allow a zero radius. And you have discussed, this was discussed a little bit in discussion already, but just to give the outline of this proof in a clear way, if you have a metric space, if you have a point inside there and a positive radius, then the ball with that radius is always open. And well, we are proving a statement that involves for every x there in omega, there exists a delta. So we have to fix a point. We call that y, since we have already used x in this as a center of ball. So the picture to have in mind is that we have this ball centered at x with radius r. We have another point y with a within this ball, and we have that distance from y to x therefore is less than s. So there's actually a good question, but I'll finish this argument and then I'll get to that in a second. So, well, what do we have to do? Well, we have fixed a point. That's our arbitrary point. That's the for every x in omega. And then we have to find a delta, because That's the existential quantifier. So what we do is we choose a delta. Delta equals r minus s, and we do that choice based on something that we know, and maybe from the picture that, okay, the distance x to y, we call it s. That is strictly less than r, and we define delta as the difference between them. And why I do this is that, well, I look at this picture, there seems to be a little extra room on the right-hand side here. That's where I should be worried, at least in the plane. And that seems to have size roughly r minus del s, at least in the planar case. So let's try that at least to see if it works. And what we want to show now is that the y delta belongs into our omega, which is this big ball bxr. So our omega that we're showing is open is indeed this ball. Well, let's keep that. So to do that, if we have done that, we've shown our choice works and we've finished our proof. So that's why we have to do this little side proof here. Well, we have to prove that that is a subset of that. So the first is a subset of the second. So we choose an arbitrary element there, z in by delta, and not less than r, there's a typo here, less than, sorry, no, this is right, this was right. This is less than delta. But what we want to show is that z also belongs into this ball. And that means that we have to estimate the distance from z to x. So let's look at the distance from z to x. Well, and to try to combine it with the distances that we know something about, namely x to y and y to z. So this triangle inequality allows us to estimate that from above. And distance x to y that was defined as s. Distance y to z was at most delta, which is r minus s. Sum of these is r, and this gives us indeed that distance x to z is less than r, and this gives us, by definition, that z is in the ball bxr. We're done. So Bowen, the thing here is that we're not trying to prove that we are in the ball centered at z. We're trying to prove that we are in the ball centered at x. So maybe if I draw this picture a little bit bigger, actually, I'll draw this with the tool. So we have one ball here that is centered at the point x. We have another point here, y, and we want to fit in a ball centered at y inside this, and I don't include the boundary here. I guess there is should be a way of doing a dashed line here, but whatever. So we want to fit in a ball here of a certain radius. And what the radius here should be, at least in the Euclidean context, is, well, the big radius minus the smaller, big radius minus this distance. So this is our r, this is our s, and in this picture, it seems like this is our r minus s, and this is our choice of delta. And so we're showing that this blue ball of this delta radius is contained in the original omega that we had, which is bxr. And to do that, we have to choose a third point. So z belongs into this is what we want to show, and we translate it into the statement that if you have a point in by delta, then actually z is also in bxr. But to do that, what we do is we take the distance y to z, and we use that to estimate the distance between z and x. So this distance here is less than, well, s plus the radius here, r minus s, and that's where we get our r. And that's where the proof really sort of geometrically comes into play, is that this showing that this ball fits inside there. Yeah. Okay, so there's a little bit of, there's 3 axes, x, y, and z, and yeah, so it's easy to get lost. I think the picture helps a little bit in that. So make sure that you're, but thanks for sticking around. The question certainly helped to focus a little bit. So see you later in another class.